theory videos of logistic regression, which leaves us with the question of how do we actually run a logistic regression in Radiant. And so this is what we're going to do in this video. And we're starting off with the generic interface here of Radiant. And the data we're going to work with today is actually part of Radiant's repository of example data sets. And we get there by loading the data of type examples. And we'll click load. And the data set we're going to choose is a famous data set called Titanic. So we're going to click on that. Now the reason why it's called Titanic is because it's actually the data of the Titanic disaster. And what it's all about is survival. So what we have, and actually as you see here, there's a nice description of the data set included with the data. And what it tells us that we have information on different passengers. Ultimately, we're interested in whether they survived, yes or no. And the other information that we could use as explanatory variables are the passenger class from first class, second class to third class, passenger sex, female or male, the passenger's age, whether or not passengers traveled with sibling or other family members, so the number of siblings or spouses aboard, the number of parents and children aboard, parch, the actual price, the fare that the passengers paid. We even have their actual names and the precise cabin that they were in on the Titanic. And the last thing we have is the port of embarkation, which were three different ones: Cherbourg, Queenstown, and Southampton. And so we have this data, which are about 1,043 passengers, or 1,042. And what we're going to try and do with logistic regression is predict or explain who survived based on these explanatory variables that we have at our disposal. And so, in order to run this regression, and obviously first we would analyze this visually, we would do a number of things. The only thing we could do for now is just actually look at some of the summary statistics. And as we can see, about 40% of passengers actually survived. Most of the passengers on board were men. The average age was around 30, etc., and so on and so forth. So after we would do our initial exploratory analysis, we would then start with the logistic regression model. And to do this in Radiant, we go into the model tabs and we click on logistic regression, which is a generalized linear model. And what it's going to ask us is, what is the response variable? And what the response variable relates to is our dependent variable. What are we trying to explain or predict? And in this case, it already correctly selected survived. And the other thing it asks us is, which level do we want to predict? And we have yes and no. What this means is that our model is going to be expressed in terms of predicting either those that survived or those that didn't survive. So we'll see how that matters in a second. And of course we have to choose a number of different explanatory variables, and we'll simply select all of them for now. And as with linear regression, we can also ask for the confidence intervals, and we'll talk about the other options later in class. And that's it for now. So we'll simply run this. So we'll click on estimate, and we get the output of our logistic regression model. So broadly speaking, then we can say that we have a good amount of statistically significant explanatory or predictive variables. It seems that all of the different explanatory variables, except for the fare that somebody paid for his ticket, as well as the number of, I believe, this p-arch related to the number of parents on board. Besides these two, and there could be a number of reasons for why they are not significant, for instance, because the information contained is redundant or it's already contained in another variable. We'll talk about all of this in much more detail later on, but for now they seem like they're not significant variables for us. And nonetheless, we will leave the model as is for now and say, so we've constructed this logistic regression model, and what does it tell us? Well, broadly speaking, it tells us that somebody in second class, so with a fare in second class, is less likely to survive compared to the reference class. Remember that for these dummies, we interpret the coefficients with regards to the reference class. So because we only have second and third, we know we also have first class, so the first class is our reference class. So somebody in second class is less likely to survive than somebody who actually had a ticket in first class. And somebody in third class is even less likely to survive compared to somebody in first class. We can later transform these coefficients so that we can talk about probabilities, but for now we only interpret their signs. And same then goes for a male passenger compared to a female passenger. The male passenger is less likely to survive, and the older passengers are less likely to survive. The bigger the party, so the amount of siblings on board, relate to a lower probability of survival. And furthermore, in terms of the ports of embarkation, both Queenstown and Southampton, compared to Charlesbourg, or what the other port of embarkation was, are less likely to survive. Interestingly, if we would look at the data, it also happens that at Charlesbourg were most of the first class passengers embarked. So we could do a lot more of analysis and making sense of these results, but for now we'll say that this is our final model. And then the next question, of course, becomes, how do we use this for prediction? And what we may do, as usual, as we did with linear regression, we could say we would like to predict for a particular passenger. And that particular passenger, so we would go into prediction and select the command function or option. And we could simply say, what is the probability? We would like to get the probability. Remember that when we run the logistic regression, what we actually predict is the probability, in this case, of somebody surviving. We could say, what is the probability of somebody that is 50 years old? And what it will give us is the probability of survival, which is about 4.2%, of somebody that is 50 years old, holding all of the other explanatory variables in our model constant at their average values. If we wanted to include their effects as well, which could, for a particular passenger, of course, not be at the average values, we could also include that. So we could say, let him have paid 100 for his fare, and we get an updated probability, which in this case is just a little bit higher than before, if he paid more for his fare and he's 50 years old. Now we could use this for individual passengers, but more likely what we would do is we would predict for an entire data set. And this can be the same data set that we just used to create these predictions, or new data really, for which we may not necessarily actually know the true survival result. Let's predict for the same data that we just used to estimate our model. So we'll select the Titanic data, and we get the predictions for all of these different observations. And as you can see, they vary significantly. And this is the probability. It's simply the probability of somebody surviving. So it's the probability of the survival variable being yes. And again, we can save these predictions. So we could store these predictions in our data set saying this is predict P. This is the predicted probability of survival. Predict P survival. And we store it. And now we have this variable in our data set. And something that we can actually do with this is use it to see how well do we predict for our actual data set with which we estimated the model. And the way we can do this is go back into the data tab and create a variable that makes a prediction for us using the predicted probability of survival. And the prediction that we need is whether or not somebody will survive. Now usually what we would do is we would say if the predicted probability of survival is 50% or greater, then we classify that observation, or we predict that that particular passenger in this case is a survivor. And if the probability of survival is below 50%, we would classify or predict that person as a non-survivor. And this is called the threshold that we'll use for logistic regression. The way we can do this is we simply create a variable that tells us, that gives us a survive or no survive response based on the probability of survival that we predicted. So we'll create a new variable which is called predict survival. And that variable will take a value of 1 if the predicted probability of survival is greater or equal to 0.5, and otherwise it'll get a 0. And a 0 relates to not surviving. And we can then run this, so it'll create this new variable for us, and we'll store this in our data set. So we can check briefly if this worked here in the overview, and it seems to have worked as we just wanted it to be coded, in the sense that a predicted probability of 96% will be classified as a survivor, and 41%, which is below 50%, our designated threshold, will be classified or predicted as a non-survivor. So using this, we can now see how well would we predict for our actual data. And we can do this a number of ways. One simple way we can do this is using the pivot tab up here. So we'll go into the pivot tab, and what we're going to do is we're simply going to compare the survived factor, which tells us how many people survived, with our actual predictions of survival. So we're going to get this table which simply tells us how many truly survived, 425, how many truly did not survive, 618, how many did we predict that would survive, 392, how many did we predict would not survive, 651. So we can I'm just going to sort this here 1, 0 as descending, so we get the yes, truly survived, and predicted survived in the upper left, and we get the predicted not survived and truly not survived in the lower left. Now this table is actually called a confusion table because it can get confusing, but the more we work with this, it's really going to be of great help for us in assessing how well our model classifies or predicts, in this case, survival. And in essence, as you may intuitively conclude, the upper left and the lower left here for us are our true positives, so truly a survivor given that we predicted a survivor, and true negatives, truly a non-survivor given that we predicted he's a non-survivor. So these are the correctly classified observations. Where we make mistakes are in these two cases. So we said somebody is going to be a survivor, but he actually was not. And vice versa, we said somebody was not going to survive and he actually did. So we can actually go and, in order to make more sense of this, express this in percentages so that we can more easily compare it or make conclusions based on this. And we can do this down here by simply selecting the percentages option. And we also need to normalize this now by either the total. We can start off with the total. And what the total will then show us is 40% generally survived, 60% didn't survive. We predicted that 37% would survive, so slightly lower than the actual, and we predicted that 62% would not survive. So now we can see how many, in terms of percentages, did we actually correctly classify. And it turns out it was about 79 or 80%, let's say. And about 20% were incorrectly classified. So we can, using the term accuracy, can say our logistic regression for our data with which we estimated it had an accuracy of 80%, meaning that 80% of the observations are correctly classified. But sometimes we're not only interested in the overall accuracy, but also in, as we talked about before, these true positives and these true negatives. Because maybe we're more interested in actually correctly predicting somebody as a survivor versus the non-survivors. And in order to look at how well do we predict the individual classes, we can normalize these percentages, for instance, by the column. So now what this tells us is, for those that survived, so survived yes, we predicted 70% correctly. For those that didn't survive, we actually predicted 85% correctly. So our model seems to be better in predicting the non-survivors compared to the actual survivors. And one way that we could tweak our model or get different results, let's say if we were interested in increasing the number of true positives, of true survivors given that we predicted survivors, we could do this by changing the threshold that we use to create our predicted survival and non-survival values. And remember, we used 50% initially, which is the standard, to predict whether somebody was going to be a survivor or not. So if we, with our model, had a probability of somebody surviving of 0.6, our threshold or our current variable then classified that person as a survivor. And if we think about it, intuitively speaking, how could we increase the number of true positives, in the sense that true survivors given that we predicted survivors? If you think about it for a second, intuitively we would probably want to decrease the threshold of classifying somebody as a survivor. So if instead of using a threshold of 50%, we would lower that threshold to 40%, what we intuitively would expect is to have a greater number of classifications in this upper left, because we make it, in essence, more likely for somebody to be qualified as a survivor. And we can try this out by simply doing that. So the only thing we need to do is create a new variable, and instead of predicting survival using a threshold of 0.5, we can use one of, let's say, 0.3. We can be a little bit more extreme for the sake of this example. So we'll go into transform and then create a new variable. And this time around we'll say predict survival 2 is going to be dependent on predict p survival, and it only has to be greater than 0.3 in order for this classifier to predict or classify somebody as a survivor. So if it's greater than 0.3, we're going to say it's going to be a survivor, otherwise it's a 0. And so we create that variable, we store it in our data set, and we now have these two different predictor or classifiers which are based on different thresholds of our predicted probability of somebody being survivor or not. And to compare this in the same way, we just now need to go back into the pivot tab, and the first thing we could do actually is save this result so we can compare it. So I'll just go back and normalize this by the total, so we see all of the total percentages, which allows us to see the overall accuracy. And I'm going to save this to the report. Actually going to delete what was here before and save this again. So just saving it to the report. So here in the report we've got that table we just created of correct and incorrect classifications. Then we're going to just compare that to our just created second predictor variable, which is survival 2, which used a threshold of 0.3. And we're going to throw out the old one. So now we get the same table, but let's see how it compares. So we're going to first look at the actual values again, sorted the same way as before. And what we can see is that we now have 348 true positives. And overall, we predicted for more people to be survivors. And that is because we set our threshold lower. So it was more likely for somebody to be predicted as a survivor in general. The question is, did we improve the true positives? And we can check that by expressing this as a percentage again and looking at the total first. And what we see is that our overall accuracy seems to have decreased a little bit. So now we're at about 75% accuracy. But have we actually increased the number of true positives? And we'll check this by, again, normalizing these percentages by the column. And yes, our actual true positive is larger. So out of all those that survived, 80% or almost 82% now are correctly classified by us. So if this was our objective, we just achieved that. However, it's usually a trade-off, of course, because basically for the non-survivors, our true negatives here went down significantly, so from about 80 to 70%. Let's just save this to the report so we can actually compare these numbers side by side. So I'm going to go back into total, save this, and so now we could compare these tables and save these two tables together. So we first got our classification using a 50% threshold, so we used predict survival as our predictor variable, and then we've got our classification using a 30% threshold to classify somebody as a survivor, which was done using our second survival predictor variable. And what we can see is that as we predicted or wanted to happen in this example, we now have a greater percentage of correctly classified survivors, but we suffered compared to the less extreme threshold in terms of now we have less correctly identified non-survivors. So in the end of the day, if we have costs associated to these misclassifications, we can optimize that. We can take this a lot further, but for now, we'll leave it at that. And that's how we run our simple logistic regression in Radiant, and also look at the results in terms of how well do we predict for our own data, and we could do the same for new data. And that's it.